is 3.7, rational functions. Rational functions. We will look at 3 different types. Can anyone give us an example of a rational function? Excellent. If it doesn't have x in the denominator, it's not a rational function. It has to have a ratio because it's rational, and the top can have x or not, but the bottom has to have x in some form or another. Yes. Actually, this will be called, this is not what the book presents, but I'm going to call it type 1. Here's the second one. I'm going to call this one type 2. And we have one more, type 3. Are these the only rational functions, type 1, 2, and 3? No, but these are the only ones we can handle in pre-calculus. Here's the third possibility. Type 3. Type 1 and 2 are very similar. Type 3, way more complicated. Now, let's try to understand what's the difference between these 3. So let's look at type 1, and look at type 2, and look at type 3, and say, I see the difference between these 2. What is the difference between these 2? Exactly. So here is, you see, the degree of the top and the degree of the bottom are same. Degree of the top is what? 1. Degree of the bottom is what? Degree of the bottom. 1. So both have the same degree. This is our type 1. So I will say degree n over degree n. In other words, I'm saying a same degree. Can it be degree 2 over degree 2? Yes. Degree 3 over degree 3? Yes. Degree 4 over degree 4? Yes, as long as they are the same. And that would be type 1. Type 2. What will you say about type 2? Exactly. Degree n, and I will say degree greater than n. So if the top is 1, the bottom can be anything but 1. Can be 2, 3, 4, and so on and so forth. If the top is degree 2, the bottom cannot be 1 or 2. It can be 3, 4, and so on and so forth. Higher in the bottom, at the bottom. Good. Now, the third one. Exactly, but it has to be by exactly 1 unit greater. So if the bottom has degree n, the top must be degree n plus 1. Exactly by 1 unit more. Anything else we don't know how to handle in this class. Okay, this is it. That's all we can do. So we can do type 1, type 2, and type 3. And in type 3, the top, if the top has degree 9, the bottom has to have degree 8. If the top has degree 3, the bottom has to be degree 2. The difference in degrees must be 1, and the top 1 more than the bottom. Here it doesn't matter. This can be 1 and this can be 10. So the difference doesn't matter. But here it's very important. Then the top has a degree exactly 1 more than the bottom. Okay? So let's start with the first one. So we chose x plus 1 over x plus 3. Perfect example. So f of x, x plus 1 over x plus 3. I'm asked to graph, of course. What do I have to do first? So the problems, and then we'll choose another problem. Yes. I have to find the domain. And this is, it starts on page 277. And the problems start on page 289. Good. So if you remember, let's summarize the polynomials. We had domain about polynomials. We had end behavior. we had x-intercepts, we had y-intercepts, we had degree, we had the maximum number of turns, we had symmetry. That's about it, right? And finding max min with the graphing calculator. So that was the whole list, right? One more time. Domain, x and y intercepts, multiplicities for the x-intercepts. Whether it crosses flat, or it turns flat, right? Symmetry, max min, and that was it, right? Okay. Here's the list for rational functions. 1, domain. And I would like you to tell me what is the domain for this function. Exactly. So negative infinity, negative 3, 0 has to be in the chart, and infinity. So this is very clear. You don't have to, for me, I'm fine if you write this or invent your own chart. I'm fine with that. You no longer have to write negative infinity, negative 3, union, negative 3 to infinity. If I see this, I know you know what you're talking about. Okay. Of course, we are going to look at 2 x-intercepts. Now I'm dealing with a fraction. When is a fraction 0? Okay, let's discuss this because this is crucial. Okay, so I'm gonna come back to this page. Okay. If I have a fraction that is a over b, I know that b cannot be ever what?
0.
Perfect. So that's one thing that we established. Now, if I want a over b to be 0, what must happen? Let's say I'm going to put it 0 over 1, which is the same thing, right? 0 or 0 over 1, same thing. Let's cross multiply. A equals, right. So for a fraction to be 0, only a numerator has to be 0. The denominator can never be 0. So a fraction to be 0, I have to set the numerator equal to 0. So coming back here and looking at this, what would you say? I want to move the 0 a little bit to the right. So what will you say? When is, you said x-intercepts, I'm sure you're going to say y equals 0, right? So when is this fraction 0? Exactly. At -1, the fraction is 0. Now number 3, of course, y-intercept. How do I determine the y-intercept? Yes. So I make x equals 0, or if you want f of 0, what do I get? Very good, excellent. 0 plus 1, 0 plus 3. So this is 1/3. Okay. Number 4. It is very clear that the function is undefined at -3. Again, this is the first rational function we graph. It will take us half an hour, but then it will be 3 minutes. But I have to explain each and every item here. So I know that the function is undefined at -3. Would you agree? So if I draw a line x equals -3, the function cannot cross it. Function cannot do this because it doesn't exist at that point. But what this function can do is this. Or, not both, or this. On the other side, what can it do? Not this, but it can do this. Or it can do this. And this happens for rational functions. This line is called the vertical asymptote. So I know that x equals -3. So vertical, that's my next step. Vertical asymptote. X equals -3. It's a line that the function cannot cross. So now I know that left and right of the vertical asymptote, the function must go to positive infinity or negative infinity, and the other side is as well. So there are 4 options. I don't know which one. So what I do is, I will not put these numbers in the chart, but I'm going to say a very close number to this will be negative 3.1 on the left, and a very close number from the right will be negative 2.9. All I have to do is think. When I plug in negative 3.1 here, what will be the sign of the outcome? Don't calculate anything, just give me the sign. Negative 3.1 plus 1. Negative 3.1 plus 3. What sign is negative over negative? Done. I know it will go to positive infinity, no questions about it. On the other side, negative 2.9. Negative 2.9 plus 1. Careful now, negative 2.9 plus 3. What sign is negative over positive? I know the signs. I know where the function is going. Exactly. Exactly. Good. Number 5. Horizontal or slant, they're not the same. Asymptote. I don't want to confuse you, but I wanted to put them there because they kind of go together. So coming back to our types, type 1, 2, and 3. These two have horizontal. Type 1 and type 2 will always have horizontal. The only one that gives us trouble is type 3. Type 3 will have a slant asymptote. So what is a slant? What is a horizontal asymptote? Exactly. And the function will either do this at infinity, not in the middle, at infinity, or it will do this on the other side, or it will come from above, from below, but it will tend to approach a number, a horizontal line. Okay, now, how do I know? So I can, for this particular function, I will cross that. I just wanted to mention it. I will cross it. It's only horizontal. For type 1, there is no slant. So only horizontal asymptote. How do I find that? So the horizontal asymptote goes with the end behavior. They go hand in hand with end behavior, which we learned in polynomials. But the end behavior of polynomials is not a line. It's positive infinity or negative infinity. But these functions, rational functions, tend to approach a line or a particular number at infinities. Okay? So now, for type 1, I would like to show you, and then I will give you the result. But I'd like to show you how we do it. Yes, this is how we do it in calculus, but they are trying to explain it in the book somehow also. So I'm going to show you how we know where does this function go. Okay. Now, what is the degree again of the numerator? 1. I want to factor out the degree. What is the degree of the denominator? I will factor out the degree. And you can say, can I do that? Yes. As long as whatever you write in parentheses multiplied by x will give you x plus 1. Yes, you can do that. So how do I do it? Let's try. Is x times 1 x? Is x over 1 times 1 over x 1?
Yes.
Perfect. So please tell me what happens at the denominator.
1 plus over 3.
Let's check. X times 1 is x. Correct? And x times 3 over x is 3. x over 1 times 3 over x. I simplify the x's and I get 3. Is that okay? Good. Now do you allow me to simplify x with x? Because we are talking about what happens at end behavior, right? Otherwise, I would have written x not equal 0. But we're talking about infinity. We're talking so far away from 0. Okay. So now, what do you think will happen to this expression? What will it approach as x approaches infinity or negative infinity? It doesn't matter. I have $1, and I want to split it with everyone on the planet. 7 billion people. How much will you get when I knock on your door to give you a piece of my dollar?
Close to 0.
Right. What will happen with $3? If I want to split $3 to everybody on the planet, how much will you get?
Close to 0.
Good. So then what does this whole thing approach? This whole expression, this one, or this one? What will it approach as x approaches infinity? I have 1 plus 0 at the top, and I have 1 plus 0 at the bottom. So what number will this approach?
0.
I have 1 plus 0 at the top, and I have exactly. And this is the horizontal asymptote and the end behavior of this function. So I'm going to write here 1. I'm going to write here 1. I'm going to write underneath y equals 1 a horizontal asymptote. And under negative 3, I'm going to write x equals negative 3 is a vertical asymptote. I'm done. Can this function be symmetric? If it has a vertical asymptote at negative 3, should I even try or check symmetry? No. But I have to write. So it's part of the whole thing. So number 6. F of negative x does not equal f of x, does not equal negative f of x, as we know. Not symmetric. I'm trying to make sense of the information I have. So bottom line, coming back here for a second, type 1 rational functions will always have a horizontal asymptote. Leading coefficient of the top divided by the leading coefficient of the bottom. So if I have x plus 1 over 2x plus 3, I have 1 over 2 as the horizontal asymptote. Okay, so let's make sense of this information and let's see how we can graph this. So let's see if we can picture this already. So follow my finger if you want. So from approaching 1, going up to positive infinity. From approaching 1, up to positive infinity on the left-hand side of the vertical asymptote. On the right-hand side, it's coming from negative infinity. It crosses the y-axis, it crosses the x-axis, and gets closer and closer to 1. One more time. From approaching 1, going up to positive infinity. From negative infinity, crossing the y-axis, 0, okay, the x-axis, the y-axis, and approaching 1. I have to graph, every time I graph a function with asymptotes, it is a must that I start by graphing the asymptotes. Ready? How many asymptotes does this function have? 2. It has a vertical asymptote. They are not part of the graph, meaning I have to graph them as dashed lines. So negative 3, you said, at negative 3, so this is the vertical asymptote, negative 3. Then I have a horizontal asymptote at 1. Perfect. Next step. One more time. From 1, approaching 1, going to positive infinity. From approaching 1, going to positive infinity on the left-hand side of the vertical asymptote. A function may cross a horizontal asymptote. That is allowed because the horizontal asymptote is basically at infinity. Here doesn't have any particular purpose. But it can never cross a vertical asymptote. It can cross a horizontal and it can cross a slant, but it will never cross a vertical asymptote because it's undefined there. Okay. Then I continue reading. Negative 1, 0 is here. 0, 1/3 is here. So now my chart says come from negative infinity, cross the x-axis. It's cross. It's a regular cross. It's a multiplicity 1. Regular cross for the y-axis, and then approach 1. So from approaching negative infinity, cross the x normally, cross the y, and approach 1. So this is f of x, x plus 1 over x plus 3. With the graphing calculator, the graphing calculator is not as smart as you are, meaning be careful how you plug it in. You must have parentheses around the top. You must have parentheses around the denominator. And you have to add the horizontal asymptote. As I said, the calculator is not as smart as you are. I'm going to use the standard viewing window. So go to Zoom 6, and then I'll adjust if it's not clear. Here comes the second function, which is y equals 1. So our function goes from 1. As x goes to negative infinity, the function approaches 1. I don't know how to make the software show the vertical asymptote. I have to look into it. There is a vertical asymptote at x equals -3. So the function approaching, the Sx approaches -3 from the left. The function values blow up, we say. As x approaches -3 from the right, the function values go to negative infinity. It comes from negative infinity, crossing at -1, 0, crossing at 0, 1/3, and eventually approaching 1 as x approaches infinity. Any questions for me?
So for the horizontal asymptote, how is it again that we find that it's 1?
Right. Let's go back. So
Because I know the top.
the shortcut is this. It's type 1, same degree over same degree, is the leading coefficient over the leading coefficient. Oh. Sorry. So because it's type 1, same degree over same degree is the leading coefficient over the leading coefficient. Now, the mathematical explanation is this. I factor out the degree. I get this binomial inside, sort of a binomial, 2 terms. This goes away because I simplify it. I know that when x approaches infinity, 1 over infinity will approach 0. As x approaches infinity, 3 over infinity will approach 0. So these are all zeros. All it's left is 1 over 1. Sx. Notice that I did not put the equal symbol. I'm saying as x approaches infinity, this expression approaches 1. Cannot say equal. This is equal. From here, what I did here is equal. But from here to write equals 1, I cannot. I have to write an arrow, meaning it approaches 1. In short, for type 1 is always the leading coefficient over the leading coefficient. But they have to have the same degree. Okay, so let's look at type 2. Type 2 is even easier than type 1. So let's choose a type 2, or we can use the one that we created. It's up to you. Okay, very good. So let's go back. Type 2 was x plus 1 over x squared minus 4. What is the first thing I do? What are the 2 keywords in this class? Yes. So then I cannot simplify, but I can factor, and I have to. So now all this discussion is the same procedure, the same steps. It should take us 2 minutes now, not half an hour. Okay. I start with the chart. I want the domain. And what is the domain? Very good. So if you just do this, I'm happy. Conclusion about x equals -2 and x equals 2. What are they? Vertical asymptotes. Very good. Once I know that they are vertical asymptotes, then I write infinities and find the sign of the infinity. There is one situation in which the function will not have a vertical asymptote at such a point, and I'll have to explain. Okay, I'll get to an example and I'll show you what happens. Okay, so as you notice, these numbers are only used to determine the sign. I'm not going to plot them or graph with them. So negative 2.1 and negative 1.9, 1.9 and 2.1. Okay, I'm going here at the factored form. Negative 2.1, negative 2.1 plus 1. You can put this in the graphing calculator as well, but I think it's easier if we just think. Negative 2.1 plus 1. Negative 2.1 plus 2. Negative 2.1 minus 2. 3 negatives then. Good. Negative 1.9. Negative 1.9 plus 1. Negative 1.9 plus 2. Negative 1.9 minus 2. Negative. 2 negatives. 1.9 plus 1. 1.9 plus 2. 1.9 minus 2. 1 negative then. Last one. 2.1 plus 1. 2.1 plus 2. 2.1 minus 2. Done. Let's analyze the end behavior. Exactly how we did it before. So now I have x plus 1 over x squared minus 4. What is the degree at the top? So I factor out x. What is left in parentheses? Perfect. 1. 1 plus 1 over x. Good. Now what is the degree at the bottom? Okay, so I factor out to x squared. I have to. I always factor out the degree, whatever it is. Okay, in parentheses.
1
Minus?
4 over x.
Of course. So when x approaches infinity, what happens to this? Good. What happens to this? What happens to this? 1. I simplify an x with an x. So this is 1 times 1 over x. What will happen to 1 over x as x approaches infinity? What happened here?
0.
Yes. And this is always the case. In type 2, always, the denominator is much stronger than the numerator. At infinities, this function will always approach 0. So y equals 0 for all type 2. Y equals 0, horizontal asymptote. Y equals 0, horizontal asymptote. I want x-intercept. It's a fraction. When is a fraction 0?
Top 0.
Good. When is the top 0?
8.
Be very careful where you put those. They have to be in ascending order. Now let's also plug in 0 and tell me what you get. That's it. Is this function symmetric? It could be. It could be because it has vertical asymptotes at negative 2 and 2, but it crosses at negative 1, 0, and it cannot be. Oops, I'm messing this up. 10, 11. Okay, not symmetric. But I have to write this. Does not equal f of x, does not equal negative f of x. So I'm giving it a shot. Let's think. Let's think for a moment. Let's think for what we see here. See if we can picture this, and then we'll put it in the graph. From 0, dropping down to negative infinity. This is a vertical asymptote. From 0, dropping down to negative infinity. Now what do we have in the middle? From positive infinity, it crosses the x-axis, it crosses the y-axis, and it goes down to negative infinity. from positive infinity, does some crossing over there, and then comes down to negative infinity. Pretty straightforward. On this side, from positive infinity to 0. Good. So what do I have to graph? What do I graph first? Absolutely. All the asymptotes have to be there. But you are right. This is an overkill. I just make a point. This is an overkill. Y equals 0 is the horizontal asymptote. But then, yes, I have to graph this. And I have to graph this. I have to write x equals -2 and x equals 2. I tried to make sense of my chart again, so let's give it a shot. Ready? Good. From 0, dropping down to negative infinity on the left-hand side of the first vertical asymptote. No problem. Yeah, I have to graph it a little bit closer. I'm sorry, my marker squeezed out there or something. So it has to be closer. Good. Now in the middle. From coming from positive infinity, it has to cross at -1, 0, which is here. It has to cross at 0, -1/4, which is here. And then it goes down to negative infinity. So here's the situation. And on the right-hand side, pretty clear. From positive infinity on the right-hand side of the second vertical asymptote comes down to 0. And this is our function, x plus 1 over x squared minus 4. Now we are ready to check with the graphing calculator. Don't forget to put everything in parentheses. Top in parentheses, x plus 1. And then the denominator is x squared minus 4. So x squared minus 4. Close. There is no need now to put y equals 0 because it's going to be the x-axis. So there is no need to add the horizontal asymptote. I'm going to choose the same viewing window. And here it comes, down to negative infinity. And of course, exactly what we expected. It's coming from approaching 0 down to negative infinity on the left-hand side of x equals -2. It comes from positive infinity, crossing at -1, 0, crossing at 0, -1/4, and coming down to negative infinity on the left-hand side of x equals 2. And then on the other side, coming from positive infinity to 0, approaching the horizontal asymptote. So when we say that the function has asymptotes, eventually we have to show that the function approaches that asymptote. So we said here that the function has horizontal asymptote. So eventually the function is to get closer and closer to it. Same thing here. So when we say that it's a vertical asymptote, eventually the function has to get closer and closer to it. Closer and closer to it. Okay? Any questions? We want to review type 1 or type 2. We want to choose a problem from the book, or we go to type 3. Okay, type 2 is the easiest because I always do this. Because horizontal asymptote is always 0. Because the denominator is so much more powerful, it will take precedence at infinities. Okay, so let's look at the slant asymptote. Type 3, last one. And this will be the end of chapter 3. So, anyone remembers what it was? Yes, x cubed minus 1 over so the problem here is that the numerator is factorable into x minus 1 and x squared plus x plus 1. You may remember this formula or not. We have not encountered it. So it's x cubed minus b cubed, which is a minus b times a squared plus ab plus b squared. And if I have here plus, then I have here plus, and I have here minus. So because of that, this function that I created is linear. So we have to find a function. I was just explaining how it works with the degrees. Sorry about that. So we have to look at on page 290, and all the functions with slant asymptotes are between 65 and 72. 65 to 72 on page 290, please choose. If you're wondering if there is applicability of these functions, the answer is absolutely yes. A lot of real-life situations are modeled with rational functions, and I can just give you several right here. So flight of a rocket, focusing distance, rational functions with graphs. Okay, that's a different thing. Transformations on that. Okay, here. Draw concentration. All these are rational functions. So multiple applicability of this function. Super important. And polynomials also. Okay, so would you like to choose? So let's choose a function that has degree at the top exactly by 1 unit larger than degree of the bottom. Okay, I will then. 68. Is that okay? So let's look at 68. In 68 we have, I'm going to write f of x. We can write r of x, doesn't matter. 3x minus x squared divided by 2x minus 2. Perfect. Now look at the degree of the top. What is it? What is the degree of the bottom? So exactly the difference of 1 degree, and the degree of the top is by 1 degree higher than the degree of the bottom. Okay, perfect. So now next thing is, the numerator is not arranged in descending order, so I have to rearrange it. I have to factor negative x and x minus 3, and the denominator 2 and x minus 1. That's my first step. No matter what function you want me to graph, I will have to factor everything completely top and bottom. Everything has to be in descending order. Everything factored. Ready? Good. Everything is the same. The only thing is that this function will not have a horizontal asymptote but a slant asymptote. And we have to find it. Either like this or like this. Okay? That's the only difference. So, domain, please. Everything but 1, indeed. Which means right away I know that x equals 1 must be. Very good. I already know right away what happens next to that vertical asymptote. It's a must. The only thing I don't have is what? The sign. So I will imagine a 0.9 and 1.1, and I will plug it in to get the sign. So 0.9, I'm sorry, 0.9 with minus in front, that would be negative. 0.9 minus 3. 0.9 minus 1. 3 negatives. Last one with 1.1. Negative 1.1, negative. 1.1 minus 3. 1.1 minus 1. Good. So then I have positive. Perfect. Good. When is this function 0? When the top is 0, because it's a fraction. There are two options. And the multiplicity is coming to place here too. Well, x equals 0 and x equals 3, therefore have multiplicity 1, so the function will cross. But if I don't change anything, I'm going to erase it. If I have this, then at x equals 0, the function will turn, either from above or from below, because it will have two solutions, x equals 0. But that's not the case here. Okay, so what are the options for x-intercepts? x equals 0 or x equals 3. These are the two possibilities. So at 0 is 0. Careful where you put those numbers. And at 3 is 0. There is no point in checking the y-intercept because I already have 0, 0. It goes through the origin. Obviously, it cannot be symmetric. It has a vertical asymptote at 1. There is no such thing. But now the final thing that I have to determine. So let's also write not symmetric. At least f of negative x does not equal f of x does not equal negative f of x. The last thing I need to do is find the slant asymptote, and I'm done. Here's how I find the slant asymptote. I go back to the original function, and I divide. How? It's up to you. You can use the synthetic division, or you can use the long division. I prefer dividing this versus this because of that 2 in front. So I recommend we divide this. I can also factor out -1. That's the easiest thing to do. So I'm going to copy the function here. So it's negative x squared plus 3x over 2 times x minus 1. So I'm going to say this, x squared minus 3x over x minus 1 is the same thing. And that constant can wait outside patiently. I don't want to involve it. It messes me up. So are they the same? Yes. Negative x squared plus 3x and 2 times x minus 1. I'm going to use either long division or synthetic division on this. And then I will incorporate the -1/2. I will multiply it. So what would you like? Would you like to do long division on x squared minus 3x over x minus 1 or synthetic division? Oh, perfect. Excellent. So what goes in the box then?
-1.
Careful?
Oh,
Yes. What goes at the top then?
1 and -3.
And 0. I cannot miss anything. So in the synthetic division, all coefficients have to be there, including the ones that are not, right? In descending order, 1, -3, and the last coefficient should be the free term, but it's not there. I have to put 0. I always copy the first coefficient no matter what. I multiply, I get 1. I perform the operations I see. The sign change was already taken care of. And then 1 times -2, I have -2. I always box in the last number. I'm dividing degree 2 by degree 1. What is the degree of the outcome?
X.
The degree is?
Oh, 1.
It has to be a line. Absolutely. That's why the requirement that the top is exactly 1 unit larger than the bottom. Because when I divide, I have to get a line. Because if the top is degree 4 and the bottom is degree 2, I'm not going to get a line. So what is the line then, or what is the answer? So remember, I have to come back. I have to copy -1/2. And now in parentheses, tell me what the answer is.
X minus 2.
Very good. Minus?
Minus 2 over x.
Good. And now I have no choice but to incorporate the -1/2. I cannot disregard it. I made it wait for me because it was easier to divide without it. But it's part of the problem. I cannot ignore it. So then, -1/2 x plus 1 plus 1 over x minus 1. Let's do this together. -1 over 2 times x is -1/2. But -1 over 2 times -2 over 1 is +1. -1 over 2 times -2 over x minus 1, I simplify the 2, and this changes to plus, and it's 1 over x minus 1. The slant asymptote is only the quotient of this division. Can anyone dictate y equals what? What is the quotient of this division? With everything incorporated, with the number and everything that is there, but I disregard the rest. 1/2 x plus 1. -1/2 x plus 1. Okay, let's analyze for a moment. Look at this line and I want you to tell me, does it look like this or does it look like this? Right, because it has a negative leading coefficient. So then I'm telling you the function must follow it. What is the end behavior of this function then? Exactly. It has to follow the slant asymptote. So coming back here, no questions. So now we are trying to make sense of this information. We are trying to, and of course I have to write it here. Y equals negative 1/2 x plus 1 is the slant asymptote. Good. So when I graph a function with asymptotes, what do I have to graph first? All asymptotes. In this case, I have to graph a slant and I have to graph a vertical. I graph the vertical at 1. So this is x equals 1. Now I have to graph the slant asymptote. So I have y equals negative 1/2 x plus 1. When x is 0, how much is y? So 1 point is 0, 1. When y is 0, I move 1. So I have negative 1 equals negative 1/2 x. Multiply both sides by negative 2. X equals 2. So 2, 0. So I found the necessary points to graph the slant asymptote. 0, 1 up here and 2, 0 here. I have to connect. This is not part of the graph. Connect and extend. It has to be dashed or dotted line if you want. So I have to write y equals negative 1/2 x plus 1. And now I'm going back to my chart and try to make sense of the information I have. So let's try to make sense of the information we have here. I do have a point, which is 0, 0. And I do have a point, which is 3, 0. So here's what I see. From positive infinity approaching the slant asymptote, it crosses at the origin and it approaches negative infinity on the left-hand side of the asymptote. From approaching the slant asymptote, it crosses at 0, 0, and it comes down to negative infinity on the left-hand side of the vertical asymptote. On the other side, from approaching positive infinity, crossing the x-axis at 3, 0, and approaching the slant asymptote towards negative infinity. This is the function f of x equals, what was it? 3x minus x squared. I just wanted to copy the original. 3x minus x squared over 2x minus 2. And this is the most difficult type. Everything is the same, but I have to determine that line. Okay, so with a graphing calculator, so let's go to y equals. Clear. I have to put the slant asymptote. The calculator will not. So I'm going to write negative 0.5 x plus 1. And the function was, parentheses for the top, 3x minus x squared. Close the parenthesis and divide by parentheses again, 2x minus 2. Close the parenthesis. I'm going to use the standard viewing window and see what happens. So zoom 6. Good? Good. I have no idea. It's stuck. I don't know. I have no idea what this is. Okay, so here it is. This is our function. It crosses at the origin. It goes down to negative infinity at x equals negative 1. It comes from positive infinity crossing at 3, 0 and approaching the slant asymptote towards negative infinity. And here approaching the slant asymptote towards infinity. Questions on this? I'll stop in 10 minutes. Just let's look at the word problem. I do have to show you one more function, at least one more of these three, in which a factor from the top goes away with a factor from the bottom, and that will not be a vertical asymptote. So let's quickly look at the word problem, and then I can show you that. Drug concentration. After a certain drug is injected into a patient, the concentration C of the drug in the bloodstream is monitored. At time greater than 0, in minutes since the injection, the concentration in milligrams per liter is given by this function. I would like you to identify it. Is it type 1 or type 2 or type 3? Of course. So the horizontal asymptote, I know this now. Exactly. So we assume that when we inject a patient with a particular medicine, we expect that eventually the effect or the concentration of that medicine in the bloodstream to go where? Away. Horizontal asymptote 0, eventually, right? Draw a graph of the drug concentration. We can do that. What eventually happens to the concentration of drug in the bloodstream? Right, and it has to have a horizontal asymptote at 0. So we can do that. Let's do it with the graphing calculator because I have this, because I like to just show you that particular situation. So 30t over t squared plus 2. So clear, 30x divided by, in parentheses, x squared plus 2. And of course, the horizontal asymptote doesn't need here because it's the y-axis. And since t is time, I'm going to force the viewing window to start at 0. And the concentration cannot be negative, so I'm going to force the y to start at 0 as well. And here it is. So I'm going to change the viewing window. I want y to be 20 with a scale of 5. So seeing this, I know that this is a rational function. I know that this is not enough. I have to go put more time in here. So let me change this to 50, so we can see it better. That eventually, look, this is what happens. Getting closer, the concentration of the bloodstream eventually will go away. And it has a maximum after a certain number of minutes. After the person gets the medication, the concentration in the bloodstream is the maximum possible, and we can determine that maximum. So I'll stop. I just want one more thing to say. So I'm going to create one function. So let's say I have this function. I only have one question here. We can graph it next time, tomorrow. I just want you to identify the degree of the top, the degree of the bottom, so the horizontal asymptote, and the vertical asymptotes. So, of course, the first thing I need to do is factor the bottom. So x minus 2, x plus 3 over x minus 2, x plus 2. This function has two restrictions. What are they? Exactly. However, after I state the restriction, I must simplify. Therefore, x equals 2 will not be a vertical asymptote, but it will be, since the function is undefined there, it will be an open point in the graph. Function is undefined, but the factor goes away with a factor from the top. That's why it will not be a vertical asymptote, but an open point, a hole in the graph. So then this simplified form is this. And the only vertical asymptote will be -2 is the vertical asymptote. What about the horizontal asymptote? The horizontal asymptote will be leading coefficient, no, it's the same degree of a same degree, it's not type 2.
Oh, yeah.
So leading coefficient of a leading coefficient, 1. Horizontal asymptote. So let's graph it and then we'll stop. So let's go to y equals. I have to, in y equals, I have to clear. I put in parentheses, let's put the original function as is. So 2 sets of parentheses, careful. Although if we have everything in parentheses, it's safe, it's okay. So x minus 2, close. And then we have x plus 3, close. And then we divide by parentheses x squared minus 4. X squared minus 4. I have to add here 1. And I would use the standard viewing window. And let's see what happens. So here's the graph. So now the question is, I claim that x equals the 2 is not vertical asymptote. As you see, it's not. How do I show that? I'll go to second and table. And second and table set, sorry, it's always going back to the default. I cannot believe how they change everything, but that's okay. So second and table, and I want to plug in 2. What will I get? If I get 0, then the function is defined at negative at 2. So I would get an error. Absolutely. Absolutely. Although, as you saw, the graph is not clear. Oh, I didn't mean that. I meant to do this. So let's graph again. So right here, when x equals 2, the function should show an open point. I'm going to zoom in. So I'm going to zoom in between 0 and 3. So I want between 0 and 3, and between 0 and 4. That's all I want to see. There is a little blip. You see it? Otherwise, the calculator will not tell us. So we have to know. You see it? It's continuous everywhere. It's just at this little thing, where x equals 2. Open point. So that is not a vertical